Okay. The rain is nice, but the temperature is it seems stormy right now, and compared to what we've been having, this is really nice weather. But you also not familiar with seeing that next to
Okay, welcome back. How did this first case problem go? I know there was some growing pains on like, this is weird, there's open-ended stuff, there's stuff that we have to do. So overall, initial thoughts on it? Yeah.
That was pretty cool.
Pretty cool? Oh, nice, thanks. I thought it was cool. I'm on the same page. So part of the reason that I'm doing this is like, especially senior design, you get a lot of problems are even less defined than what we did in class. And then senior design is even more defined problems than what you get as a career engineer, where someone just says like, build a car. No have you ever seen like car specifications of like what they describe to the engineer? What are the things that, do you know what do they describe to the engineer? What do they need?
But they usually describe like horsepower or like
Nope.
stuff like that.
No, horsepower is not a spec whenever you're designing a car. Yeah.
cubic inches or displacement.
Cubic inches is not a spec when you design a car design. What you get is material. Sometimes you're limited by material. Like you only have certain suppliers, or maybe there's a market for like aluminum versus steel or something. But that's not a spec that you're given as an automotive engineer. Any other guesses? This blew my mind when I was studying engineering, because it seemed so crazy to me. Any other guesses what you're told? If you're designing a car, what do they tell you need to design it for? Yeah. Not even what it looks like. They don't even tell you what it looks like. No. It's weird, right? A lot of times it's kind of like, if it's a Chevy, you kind of stick with the Chevy brand, right? Like you're not gonna build a Fiat. Actually, now you might, because it's Fiat Chrysler. But anyway, so whenever you're designing a car, the specs that you get are market analysis of the person that's going to buy that car. So you get things about like what kind of job the person has, how many kids they have in their family, whether or not they got a promotion that year. Nothing that has to do with like horsepower, acceleration, even like storage space. Like all of that is up to you. Of like, you have to go research this. It's not a made up person, but it's like an aggregate person of like who's gonna buy this car. So like I have a Honda Ridgeline. Probably everyone that has a Honda Ridgeline is like upper middle class, has 2 kids, wants a truck, but they're kind of nerdy. It's like, that's just who they designed it for, and that's the spec. The fact that it's got like, yeah, like certain horsepower, braking power, like all that. Hey.
Did I happen to leave my phone down here?
Right here? I have not seen a phone. I don't know.
All right.
Sorry. Good luck. So anyway, I'm kind of giving you some background about like why I do this. So the main feedback is I was flipping through, I looked at maybe a third of the projects and just kind of clicked on a few of them. I did see a lot of like hand-drawn graphs. No hand-drawn graphs. If you're gonna graph something, if you really want to do it hand-drawn, like you like the process of drawing a graph, you still need to calculate the values, and now you need a ruler to measure out where the locations are. I haven't seen anyone do that in 40 years. Like when I was an undergrad, my old school professors used to graph things by hand. I haven't seen anyone do that in a very long time. And even then, it was kind of weird. Like, it's like, why don't you just use Excel or something? So anyway, that's one thing. Most people did use like Python, Excel, MATLAB, but if you're still doing like hand-drawn, or if you're watching, make sure you're doing like computer-generated. All right, so that was just one overall thing. Then I thought it would help to like look at a couple examples of what people were doing. So one team kind of took this and thought like, hey, it's 0.1 kilograms, that's about a goose egg. Is that you guys? Okay, nice. Thank you. And this is a nice way to like take an abstract problem, turn it into like, okay, this is what I'm dealing with. And now the design assumptions that I'm making along the way, they're kind of relatable of like, okay, it's a goose egg. So I like that. That's a nice way of approaching this. So this, and there was a real like opportunity here. The squeezing force. So the question is, when does a goose egg break? Like there's a number for that. And and it's a range of numbers, right? Like it's not always 1 pound. It might be anywhere from like 1 to 5 pounds. But that's like, as you're thinking about this, it's not a lot of work, but whenever you see things like, scroll up. Whenever you're writing like definitely write down whatever you think. Like get your thoughts onto the paper, like your thought process, but go back and edit and look for things like squeezing force or likely crush. Like replace, none of this belongs here. It's an engineering like technical document. Like anywhere where you have like big, small, more or less numbers. What are the numbers that you're reporting? And yeah, I'm bringing this up because I like it, and I'm just trying to show like this is how to continue improving. Does that make sense? Because you guys are like actually here. Cool. So like in this case, I would look up Wikipedia or something like how much force does it take to break an egg, and now that's my number, and report that, and then compare that to the actual number that I used in my simulation. Another group looked at position, velocity, and acceleration. Kind of like took every value, like they did all the kinematics, put them all in there. Cool. But then when they were wrapping up, it said they used the word like efficient and velocity and then quick slowdown. So it seemed like the only graph that actually gets referenced is this one. So these don't need to be there. And again, I'm bringing this stuff up because I liked the way that you're doing it, and everyone's doing exactly what I want you to do, like trying something, like doing some engineering analysis. I'm just trying to show you, like, as an engineer, what's the expectation? The expectation is like, if you're reporting velocity, changes in velocities and that kind of thing, then the only thing you need to plot is velocity, because that's the only thing you talked about. If you want to relate that to acceleration, then it makes sense to say both of them. But rather than just like overload information, just like here's every piece of data you can possibly have, it's like an info dump of like, well, why? What's it there for? And then same thing here, numbers. Most efficient. What is efficiency? That one, people like to toss around the word efficient. What does efficiency mean in this case? Does anyone know? Yeah. Okay. So what would, because usually efficiency is some percentage. Like 0% efficient is the worst. 100% efficient is like you can't do any better. At least that's, I think that would be all we can do. I don't know. I guess when people say like improving efficient, there was 150% improvement in efficiency, but we need like some definition. Like what is efficiency here? So stopping distant, like their time to stop was your thought? It's like, okay, yeah. Yeah, so like 0, that and we could say that like the closer you get to 0 time to stop, the more efficient it is. And we have a weird definition for it. Like everything we do is divide by 0, right? 1 minus 0 divide by 0 if we're doing a ratio. So everything is infinitely or negative infinite efficiency, like negatively infinite efficiency. Yeah. But we could, like, since you're talking about like shortest time interval, like just say it stopped in, oh wait, not that one. Just say what you're trying to, like, say the number that you already calculated, like you did all the hard work. So now it's kind of like the massaging part of like, why is this work important? So just take those numbers, put them right into the document. And yeah, quickly slowing down, remain free fall. I guess quickly slow down, would that be this acceleration? Like largest acceleration? So we might as well leave that in there, right? And then what's our constant speed? How fast did we go? It's not that fast. It's like, I don't know, 10 centimeters per second. Did anyone figure that out? What was that steady state, like, velocity? It was pretty slow. I guess more homework? Is this close to what you found? 10 centimeters per second? Everyone's staring at me like, what are you talking about? Do you know what I'm talking about? For the damped motion, it like quickly lost a lot of speed and then kept moving at a constant speed. But the question is, what was that constant speed? Yeah.
I heard 41.6 meters.
So like 20 centimeters per second? Okay, thanks. But yeah, in the reports that I saw, like no one reported it, so that's why I'm asking. Like, well, what was it? And then, again, I didn't go through every single thing, but I was just kind of scanning through to see how we could continue to improve. Okay. Then so here there's a nice example of like comparing the difference in acceleration of like what is a big acceleration, what is a small acceleration. Spring was smaller, and then friction it said was the smallest acceleration. I think this was, yeah, I guess I would put the acceleration graph if I was writing this, since I'm only talking about acceleration, but or just velocity and say that the slope of the curve is the acceleration. But actually reporting like what were the numbers that we calculated, and that's great. Like, and again, it's not like a lot of work. Most of the work has already been done. It's just as you're writing, anywhere you see something like bigger, smaller, this is a crazy huge, it's like delete that and write in what's the number. Like, what are we talking about here? Quantify. You get paid for numbers as an engineer. You tell stories with numbers. Let's look at these three. All right, so I went through, showed a few examples. If you're looking at this example, what would you change for like this little, it's just a small snapshot of like wrapping up. What would you change here? Take a second. You can talk to each other. Like, what do you think? What would you change to continue to improve? It's a great start, and it has some great details, but what would you change?
No, I did. At some point, you just gotta stop going down. Yeah, you can.
Did anyone want to share what they were thinking right off the bat? Yeah.
Probably would be good to have like results, or yeah, I guess add results for each experiment, explain whether it went well, if it accomplished something.
Yeah, I really like the idea. We talked a little bit about energy and like how we could use that, and it gets mentioned for both of these. And if we're going to talk about like what energy, like how energy was taken or whatever, then report like delta E over delta T or something. Like what was the average? So we know that it went from 1/2 mv squared to either 0 or 1/2 times 20 centimeters squared. And then it took a certain amount of time. So we could talk about like how much power each one took away in that sense. Like what was average power? Yeah. But, and again, it's kind of like committing to it. Just like you did the work, be confident in the work that you did. Like the math, it works. It's not always perfect. Like it's not, especially like that spring. A lot of people had issues with like, well, what's the deal with the spring? Like, isn't it gonna bounce right off? It's not perfect, but it does work. And if you lay out your assumptions and you say, this is how I modeled it, then you can argue with how the model can be improved, but you're just reporting what you got out of it. And that's all you can do. You make your best hypothesis and stick to it and go with it. Yeah. Any other initial thoughts? Thanks. There were conversations over here. I just didn't stop in. I know you were like, you had something. Oh, you're looking for a conclusion? Yeah.
There's no like meaning towards a conclusion. It all kind of like explain what we did, and like that's where I thought you want some conclusions.
Okay.
It doesn't seem that there's a definitive like they were meaning this way.
Yeah. And so like comparing them, this one feels like it's more of a neutral approach to comparison. Just like here's all the stuff. Like now it's your turn to choose. That's one engineering approach. You end up doing a lot of projects that you don't want to do when you do it that way, because you're just like, hey, here's all the data, and then someone that is not familiar with the project is just kind of like, okay, do it this way. That looks the cheapest. You're like, I don't want to do it that way. Now I have to do the cheapest, most frustrating option. But it's fine. It's fine to like stay neutral. It's one way of like presenting information. That's the old school scientific method. It's like you're just reporting nature as it is, rather than acknowledging that you are part of nature, and in doing the experiment, you have to change. You are a part of the process. Yeah, I think this one sticks to third person too. Everything's written in third person, and I like the consistency there. I've shifted more towards first person. Do you know what I'm talking about? First and third person writing. Okay. I know we're all engineers. It's like me not write so good, but. Yeah, anyway, first person writing is nice. It kind of acknowledges that you are part of the process, that you have some kind of opinion in it along the way. And then we do have like plot here, like velocity. Cool. This one, I wanted to bring this up because one group put in the extra work of figuring out like, hey, we did separately spring and damper what if we combine them? And they presented like, let's put the spring and the damper all in one system. And yeah, just so you know, like what that one kind of looks like. So we can see like there's still that like constant offset. I think it's like mg over k, something like that. Like the distance, and then it like damps down to it. Kind of cool. All right. Other thoughts, questions on that first case problem? No? Feeling good? And so if anything that we're talking about today was like, oh, I want to go back and change the way I did something, feel free. You can edit it and resubmit it. There's unlimited submissions, and the whole goal is like to get the assignment to the point where you want it, where it's like, I'm happy with this. So feel free, you can edit it, you can resubmit. All right, that brings us to so the next thing on our to-do list for to end out Module 1. Module 1, we kind of introduced dynamics, a lot of it's review, right? A review from a lot of different stuff, and some of it's new, some of it's old, but it's a lot of like different subjects that we all brought together to talk about, like what are the definitions of dynamics, how do we use it, like what kind of tool is it, and then what does that look like in practice? So we looked at one case where we just had up and down kind of motion. For the project proposal, I'll hand out some more just little quarter sheets of paper. And here, I'll start handing those out. And here's what we'll do. And what I think for the proposal would make sense for groups is just everyone do this one quarter sheet of paper as like a brainstorming exercise. So we choose a system or so first step is like choosing some kind of like system or application. So it could be like a device or something that happened, like anything that's like moving. Examples in the past have been like running. Like what are the motions and forces that happen while I'm running? Or another example was like someone was really interested in like aerospace applications, so they wanted to look at like what is the acceleration that someone feels as they're going through like fighter plane maneuvers. But it could be like smaller things too, like how does a guitar string vibrate? Like what's like the engineering dynamics of guitar string vibrations. So that's the first step. It's like choosing that system or some kind of application. Could be for your career, for a hobby, for general interest. Next step is draw free body diagram. So take that like complicated system, turn it into simpler. It doesn't have to be like a single point, and we'll look at what rigid bodies do compared to like point masses later. But like what are the forces being applied that cause this motion? And then next step is like draw that kinetic diagram. And that's, we already kind of know at least some types of forces, like springs versus dampers versus friction. What are the effects on that motion? So it might not all be like single plane of motion. You can choose whatever you want. And it's a project proposal. So, and this is the brainstorming phase. So everybody can try it out, and then we'll choose a few and do the free body diagrams together to get some practice too. So that's the first step. It's like choose the system, draw the free body diagram, draw the kinetic diagram. So let's try that. Take a couple of minutes. What's that? Thanks. Take like 2 minutes. Think about it.
I didn't know.
Oh, you didn't get one. Here.
I didn't know the person name was.
Yeah. So this one normally everyone scans your own idea or it's like a brainstorming phase. Yeah, just this.
Oh, okay, that makes a lot more sense.
Yeah.
Sorry, I'm really,
That's okay.
I'm very like,
It's all.
I clarification.
That's all. Yeah. Yeah, I think we can add multiple people add things. One person submits it.
I think that would be
Drawing diagrams.
I can't answer those. I don't think so. It's never really, I'm pretty sure.
Yeah, someone.
control, and then it like switches the next person.
Email, scan an email. Thanks for walking me through the logistics. Actually, I do not know what this means.
I was just in some frustration. So I felt like, one for by diagram, the connection twist, and then what can they keep my box for the workforce?
Yep.
It would be tension.
I was thinking about like, gotta make sure to draw the streamline. No, the streamline. Where the parcels are built. I don't give a
We're talking about which direction. It's up from.
Because like the reactor force would technically be angles, but then you calculate.
Well, because there's the X and Y component.
Yeah.
Because it's not like.
Because the true downforce is only the y direction.
We don't really care about that. I'm just drawing one force.
On air filters.
I'm just putting that force on there. With this drag also. Downforce to drag ratio.
Oh, really? Okay. I don't know how it works.
This is not a
So basically, the A's are like this X. One,
And
one
we
is
are-
like a
we
U
have no
that's
idea.
this way, the other is a U that's this way, and there's like a slot at the bottom for this thing. So if we do like left or right,
I just drew a picture of the car.
Yeah, it's actually.
Let me see. That's what it is.
Oh, you got drunk streamer
it's on the side.
where it comes up the front. Oh yeah, you did that. And then it gets stuck on the wheel.
Oh,
Fucking design.
the positive.
The airflow gets stuck on the wheel and flies over it,
Yeah, I don't know.
over the intake, so it can't suck in the air. Whoever
We
designed
need
that.
to put up a positive rate on the car so we get more downforce.
Who's we? You.
I'm not designing the whole car,
Because my engine keeps overheating.
You should make,
And that's not my fault.
you should make like scoops underneath the car, scoop up there.
No, I've never.
What? Oh yeah, or just run it.
On purpose, it's crazy.
I hate the
I mean, it's good,
Is that
but
why our car better than that?
with an EV.
Yeah.
Well,
Ask Phil what he thinks.
I don't care.
Ask what the IC treatment is.
That's amazing, because I already know it.
Oh, well, yeah, Phil what makes sense. Why they do the car. It's so. Hey, you guys have better acceleration.
no, I mean, was.
Hey man, we got 73 horsepower.
What was that? Should overuse that.
That's not right.
How's that my fault?
Where is our yearly?
All I do is downforce, bro.
Yeah, we should improve cooling.
Yeah, come on, bro.
That's
It's like attached to the radiator at the bottom of the car.
The radiator's attached to the side intake.
Oh, yeah.
Right by the wheel. Except that air flies so far over the wheel.
You need to attach a fan to the
There is a fan on the radiator.
Yeah, water cooler.
So just like body.
Put it just like rubber
Where do we want to start?
Just drive it. Just drive it.
It's not like an EV, you don't need to pass range test.
Yeah. No, I don't. Just dump a bunch of water on them.
Dude, the range test was so light, it's like they sprinkle it like.
Why does this dump some water?
That's probably because if it rains, they're just.
Yeah, everyone's gonna drive.
Bro's gonna sign up for the driver.
Me?
Try that. I was going to.
You're too heavy.
I know.
All right. So one example
Yeah, that's why I don't.
of like, let's say someone is parachuting, and for fun, we're gonna say there's also wind blowing on this person. What does the free body diagram look like here? So we're trying to figure out what forces there are, right? Yeah. Force due to gravity. Do we want to say this person is point mass? Yeah, I mean, we can start with that, right? So we're going to take this beautiful person and just say you're a dot. So there is gravity, all right? Hopefully we have more forces, otherwise this parachute needs to get returned. Drag? How is drag? What do we want to say for drag? Is it pointing straight up? Yeah.
Would it be, I mean, roughly it'd probably be pointing straight up, but wouldn't it be like normal to all the different surfaces of the parachute?
Oh, okay. So you're thinking like parachute, there's drag along like this? Like something where there's like a distributed drag force?
I think the drag force should be opposite to velocity.
Opposite velocity? Okay.
Because if the wind's like pushing it that way, you kind of go like
Okay. Or we could say there's some drag that's at an angle because, or maybe the other way. I don't know. But like, I guess what you're thinking, I guess what I'm trying to show is the thought process was drag is happening relative wind speed. So if the wind speed is like flowing really, if it's a lot of wind, then there's a lot of force pushing you sideways. And then there's also the drag. I guess more pushing up, right? Shouldn't it be up? Something like that. Because there should be something keeping us up in the air. Or maybe that way. I don't know. I keep flipping. Wind is pushing us this way, so let's go that way. But anyway, what I was gonna... What I was gonna say is like that parachute has some big cross-sectional area, and that's our main like slowing down force. So we need a big coefficient of drag, and we need lots. The more area we get, the better our parachute is at slowing us down. And then there's also another component to that, like the force of the wind, where the cross-sectional area that the wind is blowing on is a lot smaller than the parachute. So we can break it down into those two components. It's one way to do it. Any other forces? What about tension in all the cables holding the parachute? Do we need those?
It's kind of the same thing as the drag force, because the force of the parachute is actually on the cables, and then the cables are
Okay.
putting the force on you. It's the same.
Yeah, kind of a trick question, right? Like so the cables, it's not that they have zero force. It's that for this little point mass, it's an internal force. That whatever the force of drag is, all the cable tensions have to add up to that force of drag. Okay. That's our free body. Well, did I miss any other forces? Normal force? No, not touching the ground. We're free falling. Yeah, don't need normal forces if we're not normal to anything. Kinetic diagram. What does this one look like? Pointing down. Okay, we can choose, we could say that down is positive. Is acceleration always in the same direction? Is it always down? I guess, yeah, so another like more abstract question is, how many degrees of freedom do we have when we're free falling, when we're like falling in a parachute? Or when this person is falling in a parachute? Will they move left or right? Probably gonna go down, right? There's gonna be some speed, some acceleration, some deceleration, and some constant speed. What about left and right? We have wind blowing. Not all of our forces are up and down. Something, so here, kinetic diagram, it doesn't matter like what we choose. Like if we say it's going left, but it actually goes right, then it's just a negative acceleration. But in terms of like, if I want to maintain like a y, just keep the coordinate system consistent is the main thing. So z-axis is going into the page now, if we say that it's to the left. Not that we're not really considering in and out of motion, but anyway. Cool. Then, what was another one? Did anyone else want to shout out another example? Yeah.
A aircraft doing a 45-degree steep turn.
What is a 45-degree steep turn?
It's a aircraft is doing a 45-degree bank in a constant turn while maintaining constant airspeed and altitude.
Oh, so you want three-dimensional motion.
Could be simplified into two for the sake of this, but
No. So this is 45 degrees, and then we're going around in a curve like this, something like that.
yeah.
Okay. What do we think here? What force? Well, first off, do we want to do point mass, or do we want to say like, no, this plane, it's a plane, we need like rigid body? Like, is point mass enough to figure out what's going on here? It
Could be simplified, but you've got different amounts of lift on both wings.
Yeah, but all that is just creating like the bank. So if your question is like how much force is on each wing, then we have to consider like what are the torques created to maintain this position. If you're trying to figure out like what is the acceleration that the pilot feels, then doesn't matter how the the turn is happening. You're just trying to figure out, like, as you go around in this circle, what's happening to the person inside. So we could start there, right? Like, say point mass is moving in this curve. What's happening there? So what kind of forces do we have on an airplane? Are we out? Oh, we're out of time. Next time. All right. So there were some great questions that I should have covered first thing. We can talk about it on Friday, but all of this is for Project 1, where Project 1 is like a brainstorming, what are we going to do for Module 5? So keep track of this paper, or get a new one if you want to start over on Friday, and then everyone will scan it and will submit like all those papers as a group. Yeah. That's what we're doing. Yeah, right now. Yep. And getting some practice, like how do we do free body diagrams? Like what kind of forces we can consider.